All right, good morning, everyone. Welcome back to Legion School. So sorry we had to miss Monday. We realized that it was President's Day, so we decided to give everyone the day off. But we're back today. We missed our low-level session for this week, so we'll definitely have one next week on Monday. Sean will be giving that. And today I'm going to talk about task operations. So in the past, what we've done is we've walked through how the runtime works. We've done how all the different kinds of Legion operations exist, and then we walked a little bit through the different runtime services that are provided in terms of, message managers and processor managers and memory managers and so forth. And today, what I want to do is sort of start to close some of the loops that exist by talking about the actual tasks that we have inside of Legion, how we create application tasks, how we execute them, and so forth. And once we've got that in place, we're going to be pretty much mostly complete in terms of the control structures inside of the high-level runtime, at which point we'll be able to move into the region tree and start talking about how Legion tracks data and looks at data dependencies and so forth. So today, think of this as, wrapping up some of the control structures and actually starting to look at the tasks that we actually create for applications when they run. So the first thing I want to look at today is I'm going to jump into this new task or this new file that we haven't looked at before, or we may have looked at it briefly, but just very shortly, and that is this legion task.h header file. So let's open up this file here. The legion task.h is effectively the file which contains the declarations of all the different kinds of task operations that we have, or task objects. So you recall that in Legion, pretty much everything that we send through our operational pipeline has to be of type operation. Well, the base class of all of our tasks, we're actually going to have a base class for all of our tasks. This is going to be a class, this task op class that I'm highlighting here. And you'll notice that this extends the speculative op class that we looked at in a previous lecture. So the speculative op class is a special kind of operation that supports speculation and predication and so forth. But that extends the operation class, and that's how we are going to have all of our tasks extend the operation class. You'll also notice that our task extends this task class. And for those of you that are familiar with the legion.h header file, just to refresh everyone, I'm going to hop back here and show you that this same task object is coming from the original legion.h header file, which defines our actual interface. If I search for a class task, here it is. It's a special kind of mappable object, which contains a whole bunch of fields that we make available to our mappers to actually set things on. So we're extending this object as well so that we can actually have all these fields in all of our tasks. So when we pass them to mappers, the mapper will have all the things that it needs to be able to reason about this task object. Okay, so jumping back to legion task.h. So we have this base task op class, and the idea of this task op class is really it's going to be an abstract class. I'm pretty sure there's some pure virtual methods on here. Yeah, you can see there's a bunch of pure virtual methods. I can highlight a whole bunch of them here for you that are all going to need to be implemented by some of our base classes that actually implement real kinds of tasks. But this is just going to pretty much serve as sort of a utility class which has a bunch of methods on it for doing various things that we're going to need to do as part of task execution, like recording all the different kinds of field spaces and index spaces and stuff that are created when we run tasks, and tracking fields, and all sorts of interesting things. But so that you can think of this task op class as just providing the base class with some basic utilities that all of our different kinds of tasks are going to need to support. Okay, let's see let's actually walk all the way through the hierarchy of classes, of different types of classes that we have for different types of tasks. So let's see who extends this task op class. So if we search for task op, okay, here we see our first kind of class which extends the task op class. And this is the single task class. And the single task class is really going to be it's also going to be another abstract class. It's going to have filled in some of the details, but you'll notice there are some pure virtual functions on this single task class. But the idea of the single task class is it's going to represent a fusion of a single application level task running at some point in time. And so we're going to see there are a couple different instances of this single task class. And those of you that may remember from an earlier lecture, this single task class is actually what gets type-deffed to a context, or actually, more specifically, a single task pointer becomes a context. Whenever you run an actual task on a low-level processor somewhere from the Legion high-level runtime, it will have an associated single task object that tracks all of the metadata associated with that task as it's running. So as it's launching off child tasks and doing other operations and so forth, one of these single task objects will be the enclosing context in which all of those sub-operations are being generated. So the single task class is going to be very important, but we'll come back to that in just a minute. Let's finish seeing all the places where this, we're going to do a breadth first search. So we're going to see all the places where this task op class is used, and then we'll move on and look at where single task class is used a little bit later. Okay, so let's continue searching for public task op. Okay, and we'll see that there's another kind of class here. This is the multitask class. So instead of having a single task, we can have a multitask object. And this multitask object is also another abstract class. You see it has a bunch of pure virtual methods in here for all the different things that need to be implemented for a multitask. And a multitask is really just going to be an abstraction for having a collection of a bunch of single tasks that we're going to track with inside of just one object. And as an example of this is if you've done like an index-based launch, we're going to see that there's going to exist an index-based task that's a subtype of the multitask class and so forth. Okay, and it turns out that these are the only two kinds of task ops, the only two classes that extend the task op class in the Legion high-level runtime. So we have single tasks and we have multitasks. You can think of them as one-off tasks and then collections of a bunch of tasks all grouped together into a single object. Okay, let's continue our traversal of the type hierarchy here of all the different kinds of classes. Let's jump back to where we saw single task. So here's single task. Let's see what kind of single task objects we have that exist inside of this class, or inside this file here. So if I search for public single task, I went a little too far. So here's the first kind. This is an individual task. So an individual task, you can think of this as an object that always gets created whenever we do a single task launch. So if you remember from the Legion header file, we have a way of executing a task, just launching off one task to be run somewhere. And what we'll do is when one of those whenever we launch one of those tasks, what we're going to do is we're going to make one of these individual task objects. So an individual task means we're only going to have one instance of this task run on one processor at one point in time, and it's going to implement the single task class interface so that we can, we launch subtasks and so forth. They're all going to do the right thing. Okay, so we can have an individual task. What other kinds of tasks, single tasks, can we have? This next one is a point task. So you can see we have this class called point task, which extends single task. And again, this is going to implement the same interface as individual tasks. So when it actually runs, it provides all the same interfaces that the single task class needs for actually supporting, launching of sub operations and so forth. So this point task is designed to be a little bit more specialized of a single task. It's going to operate within the context of, for example, if you do an index-based task launch, at some point we are going to enumerate all the different points in that index space, and we will create a separate point task for all of those different tasks, and they will each run at some place inside the machine. And we will have an associated point task class to represent each of those different task invocations that are going to be running. So this point task is just another kind of single task object. Okay, and let's see, there's one other kind of single task. And so what you see is there's this third kind, which is a little bit less important. It's called a wrapper task. And you'll notice there's a comment here, and the wrapper tasks are kind of a little bit of a hack, but maybe not so much. The idea of the wrapper class is that in some cases we actually want to have an object which is going to provide the same interface as the single task for a bunch of different operations, but we don't want it to actually progress through the pipeline. And the reason for that is that, sometimes we're going to need to have ways of executing a task without having it do the whole operational pipeline. And so to give you an example of that, we can actually look at who extends this wrapper class, and we'll see exactly what I mean when I say we don't actually need to traverse the pipeline. So this first case is is called a remote task. So remote task extends the wrapper task type. And the reason we have remote tasks is that sometimes, usually when you start running a task and it launches off sub-operations, those sub-operations like to track or the subtask like to track its parent, the parent task, the single task that it was launched within. But in some cases, when we move tasks to remote nodes, we're not going to immediately have a remote or a parent task that we can immediately track. And so this remote task class is designed to provide a way of creating objects which can serve as a proxy for the parent task, sort of track all the metadata that's necessary for the parent task without needing to actually walk all the way through the pipeline and do stuff. So it provides the same interface as a single task, but it doesn't necessarily, it actually doesn't ever go through the pipeline the way a normal task object would go through the pipeline. So that's the first case where we have sort of a wrapper task, is this remote task. We'll talk a little bit more about these later today. There's actually another kind of wrapper task. There are these inline tasks. And again, this is another case where we actually want to have an object which is going to have the same interface as the single task class, but it's not actually going to traverse the pipeline the way a normal operation would. And we use these inline task classes whenever a mapper actually requests that it should be inline directly into its parent task context. So one of the options on mapping a task in the mapper interface is to actually say that you want that task inline directly into the parent task's execution. So you want to run on the same processor the parent task is running on and use all the same physical instances that the parent task is using. So if you ask for that, we're going to create one of these inline task objects, which is going to provide the necessary interface for actually executing that subtask right in line inside of the parent task's context. And so again, this is a case where we don't actually need to traverse the whole operational pipeline. So anyway, those are two examples of this wrapper task class. For the most part, you probably won't need to look too much at this wrapper class or the inline or remote task classes, but if you do find yourself in there, you can at least remember that they don't actually go through the operational pipeline. They're more just about providing the right interface. Okay, so we looked at all the different kinds of single tasks. Right, so we had single tasks, which were extended by the individual task and the point task and the wrapper class, and then wrapper class is extended by remote and inner tasks. Let's actually continue our breadth first traversal. Let's look at what extends the multitask class. So there are two classes that extend the multitask class. The first is an index task. Every time you do an index-based task launch, we're going to end up creating one of these index-based task launches, and it's going to implement this multitask interface. So it's going to have all the information necessary for executing an index-based task launch, being able to run, effectively track a whole bunch of different tasks that we're launching all at one time, and doing analysis for them, and then eventually spawning them out into point tasks and running them somewhere. So that's the first kind of multitask. The second kind of multitask is one of these slice task objects, which I'm pulling up now. And the idea behind a slice task is it's going to be a subset of a multitask object, but still an object that's capable of moving, or representing a whole bunch of different points inside of an index-based task launch. Probably not the whole thing, but just a sub part of it. And sort of the motivation for this, actually just to show you where we're going to actually create these slice tasks, I'm going to jump back to Legion header file, and we're going to go look at the mapper interface real quick. There's a mapper call in here called slice domain. Here it is. This is one of our mapper calls. And the idea behind the slice domain mapper call is to say, given we have this task and some domain of points that we want to launch a separate instance of that task for every one of those different points, how do you want to split the space of points up into what we call slices that are going to actually be possibly moved to different nodes and executed, and then spawn each of the different points inside of those slices on another node. So this mapper call allows you to chop up the index space of tasks and break them into smaller slices of tasks you can then manipulate by sending those slices to different locations inside the machine. And the idea from the internal perspective is that for every one of these slices that gets requested by a mapper, we're going to create a new slice task object to actually track the subset of points that are supposed to be moved around and executed together. And that's what a slice task object is going to represent. And so it comes directly from this mapper call terminology that we have back in our original interface. Okay, so I'm jumping back to Legion tasks.h. So if I come back to search for multitask, we have our original index-based task launch, and then we have our slice slice task objects, which represent subsets of points inside of an index-based task launch. Okay, that pretty much covers the entire set of different types of tasks that we have inside of the Legion header file. And so what I want to do is actually start looking at how some of these different task objects actually get used, and then how we actually progress through the task, the operational, or how tasks progress through the operational pipeline. You'll see that we're going to see that they have a couple more stages than the normal operations do. And part of that has to do with the fact that all the operations that we've looked at up till now have been local to a node. Effectively, wherever you've launched an operation, it's always run on the node where it was created. Tasks have a slightly different property, which is they're actually able to migrate across from one node to another. So we have to have ways of reasoning about tasks moving around inside the machine. And what we're going to see is that specifically, there are only 2 of these tasks that I've mentioned here this morning that are actually allowed to move around. But it influences, how all the different kinds of tasks move through the operational pipeline. Okay, so before I move on, does anyone have any questions? I guess there aren't that many people here today, so I'm going to keep going. Okay, so let's actually take a look at what happens inside of a trigger execution call for one of these task objects. So you'll recall that I'll actually preface this by saying that most of the tasks, implement the very generic kinds of or the basic operational or stages of the operation, the base operation class, in terms of doing things like dependence analysis and triggering mapping and so forth. So if I actually search here for trigger dependence analysis, this is the one on the slice test. Let's actually see if we can find. Right, so an individual task, is going to provide an implementation of trigger dependence analysis, which is going to check for all of its region requirements to register dependencies and all its region requirements, just like copy ops and map ops and all the other ones that we've seen for trigger dependence analysis. So those kinds of stages are pretty standard in terms of the tasks. They're going to follow most of the basic operational pipeline. The place where things are going to get a little more interesting is going to be in the trigger execution call that we normally get saying we're ready to actually map and execute this task somewhere. And so what you're going to see is there's going to be 2 versions of trigger execution, or 2 places where trigger execution are different. And you see there's one version of trigger execution on this. I'm scrolling up here to show you which class this is on. This is the single task class I'm highlighting here. And if we scroll down, we see it has its own implementation of trigger execution here. And then there's going to be a separate implementation of trigger execution for the multitask kind of class. You see these are concrete. So we're going to have effectively just 2 kinds of trigger execution, one for single tasks and one for multitasks. And remember, these are only called once these objects are ready to map and all of our mapping dependencies have been satisfied and so forth. So at this point, we know we're ready to map and run these various tasks. So what I'm going to do is actually dive into these 2 trigger execution calls today and actually look at what they do and how they operate for single tasks and how they differ for multitasks. Okay, so let's jump back here. We're going to go into Legion tasks.cc, which is the class which contains all the code for all of our different kinds of task objects. So let's actually search here for trigger execution. Okay, so I brought up the trigger execution call for the single task class. And so what you'll notice is that this call, because it's the same for every single kind of single task object, it means that it can be used across the individual task objects and the point task objects and so forth. And what I want to do is there's actually a lot of very high-level logic going on here that has a pretty good indication of how these various task objects are, both mapped and executed and launched onto the various processors that we're going to run them on. Okay, so I want to actually walk through this function in a fair amount of detail. And the first thing you'll see is there's a little bit of logging here, but the first thing we're going to see is we're going to check to see if we're remote or not. So you can see there's a call that tests whether or not our object has been moved to a remote node or not here. So recall the task can actually be migrated around by the mapper. The mapper can say to send tasks to remote nodes and so forth. We're doing a little check here to see whether or not we're remote. I'm going to skip the is remote case first because it actually is contingent upon actually being moved remotely. So what I want to do is walk through the not remote case. So this else case first. Let's walk through this, and we'll see how tasks might actually be moved to a remote node, and then we can come back and do the remote case. Okay, so in the case where we're not remote, the first thing we're going to do is check to see if we've already been pre-mapped, and if not, we're going to pre-map our task. So we do this is pre-map check. If it's false, then we're going to have to do this pre-map task, which is going to check to see, which is actually going to do the traversal from where all of our we requested privileges on where our parent task had privileges to where we requested privileges and so forth. It's possible that this pre-map task can fail. At least right now, it won't be in the very immediate future, but at least for now, it's possible that it can fail. So if it returns false, we're going to need to set our success variable to false. Remember that, just to refresh your memory, remember that trigger execution takes a Boolean saying whether or not it actually succeeded or not. And of course, if you fail, we're going to end up putting this operation back on the list of tasks that are ready to map but haven't actually mapped. So that's why we're going to track this success variable to see whether or not we actually successfully completed all the operations inside of trigger execution. So if we fail to pre-map, we can come down here and set success to false, at which point, we're going to return success whether we succeeded or not. But in most cases, we're probably going to succeed. Okay. So I'm going to skip the special case here if we're doing a must epic launch. That's a very special case that we're going to skip for today. In the more common case, what we're going to do is once we've done our pre-mapping, what we want to do is see whether or not the mapper has requested that we should locally map or not, and then if we haven't, we're actually going to need to see if we're going to be sent remotely or not. So let's see. So let's handle these cases one at a time. So this first case, let's see if the mapper has asked us to locally map. So in tasks have this notion of local and remote mapping from the mapper interface, which if you use Legion, you're probably familiar with. And the idea is that just because we're going to send a task to a remote node doesn't mean that we don't already know what the correct mapping for that task operation is. So it's possible that we might actually want to map our task on the node where the task was originally created, and then actually send it remotely and execute it on a remote node. But we can always map it on this local node. We call that locally mapping. So, and we allow the mapper objects to actually control whether or not tasks are locally mapped, because there's a trade-off there in terms of serializing the mapping dependence analysis versus actually moving a bunch of metadata to a remote node to actually do the mapping on a remote node. So in this case, this is checking to see if our mapper has actually asked us to be locally mapped. And if it has, we're going to check to see if the processor on which they're going to send us is actually remote or not. There's a little test here on the runtime. There's a little operation that the runtime supports. This test is local. You can give it any processor. And the runtime will tell you whether or not that processor is local to the node that we're currently on. So we check to see if the answer is no. So if it's not going to be, if the processor is not local, which means we want to map locally, but we're going to send it to another node, we actually need to do that mapping now. So there's a method here called perform mapping, which is actually going to go and map all the different regions for this task before we actually do anything with it. And it will map all those regions. And then once we've done that, we can actually do this distribute task call, which will actually send this task to the remote node that the mapper, this target processor where the mapper has requested this task be sent. So we're going to look into detail at this, these perform mappings and distribute task calls in a minute, but I want to finish getting through this logic of of what's actually going on here. Okay, if either of these two cases were not true, either we're not locally mapping or we're not, or the processor we're sending to is not remote, we can actually know that one of two things is possible. Either we're going to remap things remotely if this is false, or we know that we're going to map things locally, but we're actually staying on this local node. We're sending it to another processor within the same node, so we don't have to do the mapping right away. In either of those two cases, we come down here to this else branch. This else branch, the first thing we try to do is actually try to distribute the task. You'll notice that this distribute task actually returns a Boolean saying whether or not the task that we sent to another node is still local or not. And you can see we test that actually up here in this distribute task. Effectively, if we know that the target processor was not local, then we know the distribute task better have sent things away, which is why we have these asserts up here. Down here, we may have been, we're not sure if the mapper had said that if we're going to be mapping remotely, then we're going to not know whether or not we're going to send this task remotely or not. So we do this distribute task call, which is going to either send the task away to a remote processor. It may send it to a processor on a remote node. It may send it to another processor within the same node. It may choose to keep the processor or keep the task on the local processor. If it either chooses to keep the task on the local processor or the task is going to stay on another processor within the same node, this distribute task will return false, and we're going to move. Or sorry, I got that backwards. If either of those two cases is true, if we're still going to be local on the local processor, then we know we're going to be continue to be on this processor. Otherwise, if we sent it away, then we're going to be done because we distributed this task to another processor and we're done with our triggering of our execution. So if distribute task is true, then we're going to jump into this if block, and we're going to check now we can actually try to do our mapping. If our mapping is going to succeed, then we're actually going to launch our task, and we can actually know that we've kicked off our task onto this target processor that the mapper asked us to map onto. Otherwise, if we failed to map, we're going to record that our success has been set to false. And notice also just up here that I failed to mention this up here, but we also checked for this condition on perform mapping in the case where we were mapping locally and then sending our processor or sending our task away to a remote processor. So we can also fail to map here, in which case we set success to false, and then when we return, we will mark that we failed to map. Okay, so that covers the local node case. You can see we do a whole bunch of operations on the local node case. We do some pre-mapping, then we figure out whether we're going to map locally and then distribute ourselves, or whether we're going to distribute ourselves first and then map and then launch ourselves, and so forth. So that all occurs on initially. This will always occur. This path will always execute at least once for every single one of these tasks on the local node. Every time you launch an individual task, we're always going to execute this task on the local node, this path, ensure execution on the local node exactly one time. Okay, now it's possible that this task has actually been sent away to a remote node. There's a whole bunch of machinery inside of this distribute task call here that I'm glossing over right now that knows how to package up all the metadata for tasks and send them to a remote node, and then have those tasks actually get unpacked on remote nodes, and then created and then put it back into the operational pipeline on the remote nodes. And if we have some time today, we'll actually dig into that. But the important thing to know is that we've actually already looked at some of that machinery already, which is those this distribute task call actually relies pretty heavily on those message managers that we saw in an earlier lecture to package up all the metadata for sending a task to a remote node, serializing it, sending all the data across the interconnect, and then unpackaging it on the remote node and putting the operational task in the pipeline. So we have time today. We'll actually go into this distribute in a little more detail. Let's actually look now at the remote case. This is the case. So in the case where we actually do send a task remotely, what we'll do is we'll unpack that task and we'll immediately mark that we've already done our dependence analysis and we're ready to map and so forth. At which point we can immediately call trigger execution on this operation, which puts us right into the pipeline on the remote node to actually be able to start operating this task. And actually, since we're here, we might as well actually walk through this very briefly just to show you the high level of how these tasks get moved to remote nodes. So let's actually dig into this distribute task and see where it takes us and how it pops us back out into this trigger execution call on a remote node. So let's look at distribute task. It's actually okay. The distribute task is very simple. We have a little condition here. Check to see if our target processor is our current processor. If not, we're going to ask the runtime to send our task to a remote to our target processor, in which case we'll return false, saying we've been moved to a new node. Otherwise, we return true and say, our task has actually been distributed. Notice that this only applies to these individual task calls. There are a bunch of other distribute calls for point tasks. We're never sent anywhere. We're not allowed to be moved. We already know where we mapped. We'll look at point tasks in more detail later. You can see there's lots. We'll look at some of the distribute calls for things like index-based tasks and slice tasks a little bit later. But for right now, just think of, let's just work through the individual task case where we have a single task that's been launched, and we're walking it through this operational pipeline. So we've ended up calling trigger execution, which invoked distribute task. We check to see if the mapper has changed our target processor to be not the same as our current processor. In which case, we're going to send this task to another processor. Let's actually see where this call takes us. We're going to go look at runtime send task. So runtime is always in runtime.cc. We're going to go back here and look at runtime.cc. Okay, I'm going to search for runtime send task. Okay, and you'll notice that this send task call gets a very generic task op. It's not specific to any of our different kinds of tasks. Effectively, there's going to be a way of doing the same operation for every kind of task. So the first thing we're going to check to see, notice we're going to look for our processor manager to see if we can find this target processor that we're going to look for. And of course, if we find it, then we know that the task is being sent to a processor on the same node that this runtime is managing. In this case, it's a very simple to update this task. Effectively, we can change its current processor to the new target processor that we're sending it to, and then we can immediately add this task to the ready queue for this processor that the mapper asked us to send it to. So it's very simple to send tasks to another processor inside of our same node. This will get put onto the ready queue, and once it gets put on the ready queue, the mapper for that processor will know that it exists, and then it will be able to wake that task up and start running it and calling trigger execution, and we'll be right back where we were. The other case is the case where we weren't able to find it in our set of local processors on this node, in which case we need to actually send this task to a remote node on another node. So what we're going to do is we're going to find the message manager for this target processor. So this lookup find messenger will just take our processor and look up the message manager for the node where that processor exists. We're going to create a little serializer object, which is going to provide a buffer for packaging up all of the different data, or all the data for moving this task to a remote node. We're then going to do the actual packaging of this task. So we serialize a couple of different operations in this buffer. We package the target processor that we're sending. We're going to package the kind of task that it is. And then we're actually going to call this pack task call. And I'm not going to dig into pack task today, but what we do is we pack in the buffer, the serializer that we're going to use to serialize up all our data. And we package in the target processor that we're getting sent to. And then we get back a Boolean saying whether or not we're supposed to deactivate this task once we've sent it away. And so once we've packaged up everything into one of these buffers to represent this task going to a remote node, we ask our message manager to send this task to a remote node, and we say flush this call immediately, this message immediately, because we want to get it sent over there right away. We don't want it being deferred. And of course, if we were asked to deactivate the task, then we can call the deactivate method. We'll see a little bit later where this deactivate call comes in. So let's actually bounce through the message manager and see how this message gets sent. So if we search for message manager send task, okay, we see what we're going to do is we're going to package this message into our buffer. We're going to give it a tag, which is task message, which means this message contains a task that we're going to want to unpack and execute on the remote node. And we know that flush was set to true, so that's going to tell this package message call to actually send this message immediately. Now, we've seen that this package message call, we actually looked at this in a prior lecture, so I'm not going to dig into it. But we know that it does is it packages up all these messages and sends it to a processor on the remote node. And eventually, what will happen is there's an unpack method, which will actually unpack these messages as they come off the wire on the remote side. And here's here's the case handling for all of these for message managers. They have this handle messages call where we iterate over all the incoming messages, we unpack their kind, and then we unpack all the messages. So not surprisingly, task message is the first one in the case of the different kinds of messages that get sent to remote nodes. And what we see is what we do is we just turn around at the runtime, say, here's the buffer of all the stuff that you packed up when you packaged that task. Why don't you go ahead and handle that task that we just sent to a remote node? Let's actually look at where this handle task call comes back out into the runtime. So we search for runtime handle task. Okay, we see that what we get is we get this buffer, this deserializer, which represents a buffer that needs to be unpacked. And what we do is we turn around and call a static method on this task op, which is unpack this this task object. Let's actually go back to legion tasks.cc and see where this this call actually gets unpacked. So coming back to legion tasks.cc, search for task op, unpack. What was it? Unpack. Trying to remember what it was. I'm sorry, I just had a brain freeze. Let's remember what this process unpack task. Sorry about that. Make sure I remember this. Process unpack task. Coming back to legion task.cc, we are searching for task op. Process unpack task. Here we go. Okay, and you see we get our runtime that's doing the unpacking, and we get our deserializer buffer that contains our task that we're supposed to be unpacking. So you see the first thing we do is we unpack the processor that we serialized into the buffer, which is the first thing that we did. This represents the processor which we're going to actually send this this task to. And then the second thing that we unpack is the kind of task. And this tells us what kind of task we need to actually task object to create in order to do the unpacking. You'll notice that there's only two kinds of tasks that we're actually allowed to send remotely, and that is individual tasks and slice tasks. So there are two cases in this switch statement. And right now we're in the individual task kind. We'll look at the slice task kind a little bit later. But you should always keep this in mind. There are only really two kinds of operations that get moved remotely. There are individual tasks and slice tasks that can move around the machine. We'll find that index index tasks never actually leave the node they're created on. They're always sliced into pieces before they get moved, and then only the slices get moved around the machine. Similarly, the point tasks will always get either always enumerated on the place where their slice task is being mapped, or they're enumerated on their origin node and they get moved around inside one of these slice tasks. So really, only individual tasks and slice task objects are allowed to move around the machine. Okay, so we're in this individual task case. So what we're going to do is we're going to ask the runtime to give us a new individual task object that we can use for unpacking this, for representing this task to do the unpacking. So you'll recall that this is just a way of getting an available individual task operation from the runtime. So it gives us back one of these individual task objects. We ask it to unpack itself, at which point, once it's unpacked, we add it to the ready queue for the particular target processor, this current processor that the mapper asked us to send that task to. And once we put it on the ready queue, it's back in the pipeline for that particular processor. And once that happens, it's up to the mapper then to pick that task to schedule. And then actually call trigger execution, and we'll be coming right back into single task trigger execution, just as if we were on the origin node, except this time we are on a remote node. So that's how we move tasks. That's how this distribute task call that we were looking at here earlier can actually result in say an individual task object being sent to a remote node. Okay, and once we've sent the task to a remote node, this remote call will always return will return true. So as soon as you've sent the task remotely, it will always return true that it's been moved remote. There's one exception to that, which is actually these tasks can actually be moved around a couple of times. So notice one of the interesting things about this is that this pipeline is that it actually allows mappers to move tasks around several times. So for example, let's say that we have already been moved remotely. The mapper, changed our target processor and actually, decided to send us to a remote node. It's possible that the mapper on that remote node said, whoa, I've got way too much work to do. I don't actually want to handle this. I'm going to send it back or I'm going to send it to some other processor on the machine that I think has less work, maybe another processor on the same node or something. This is why we always call distribute task before we actually do anything. the mapper can always change that target processor that they want to be mapping on. And if they do, we might actually end up moving a task around to multiple different processors before we actually end up mapping and running it. We always call this distribute task before we end up mapping and running one of these tasks. So this distribute task, will always check to see whether or not that target processor is the same as our current processor, and if the mapper has asked us to go to a remote node, we'll always end up moving our task to another node. And so it's possible that we actually end up bouncing around a couple different processors inside the machine, depending on what the mappers decide to do in terms of moving this task around inside of the machine. But this pipeline, is flexible enough to handle mappers continuing to move things around until they're ready to actually map them. Now, this is remote cases is pretty much always going to be true once we send things remote. The one exception in that case is it's actually possible for our task to get sent back to the original processor that it was actually on in the first place. And if that's the case, we always keep track of the origin processor where we actually started. And if we ever make it back to that to the processor where we actually started on, or where this task was created, then we'll know that we're no longer remote, and we'll be able to come back down into this path down here. But in this case, we'll already have pre-mapped and so forth beforehand, and so this case will actually look a lot like the remote case if we get sent back to our origin processor. Okay, so let's actually do this remote case in a little bit of detail here. So again, we always call distribute task to see if the mapper has asked us to get moved around before we do anything. So if it's asked us to move ourselves to another processor, we can do that first. Let's say they actually decided not to move us. If they didn't move us to another processor, well, in this case, we check to see if we locally mapped or not. So if we locally mapped, that means we actually did the mapping on the origin processor where we originally started, in which case we know we're remote and we've already mapped. Therefore, we don't actually need to do any mapping. We're already ready to launch this task. So at this point, we can already launch this task immediately on this local processor. The alternative case is that the mapper chose not to locally map us, in which case we need to do our mapping and then launch ourselves to actually be able to run on the target processor. And of course, if we fail to map, we have to set success to false, and then we're going to return false. And of course, the other case here is that if distribute end up being false, then we actually, we're sent away to another processor, either on the same node or a remote node, in which case we don't need to worry about actually doing anything after this distribute task call in the remote case. Okay, so that is single task trigger execution. And you can see there's a lot of interesting logic going on here, but this is probably one of the most important function calls inside of the Legion runtime, because it actually allows us to see a lot of the different stages of how tasks go about being executed as they move through different parts of the machine. So in my remaining time today, what I'm going to do is we're actually going to jump into these perform mapping and launch task calls, just so you can see what's in there today. And the next time we'll do is we'll actually look at the multitask version of this trigger execution call, so we can actually see how it differs from the single task case. Okay, so we looked at distribute task for actually sending tasks to remote processors. Let's actually look at perform mapping and launch task in the little bit of time that we have left today. Let's actually search for perform mapping. So I'm going to do this for the individual task case for today. And we're actually going to see, we can see that there's a lot of similarities between the individual task and the point task version of perform mapping for the various kinds of single tasks. Okay, this perform mapping call for individual tasks is actually pretty simple. We're going to see most of the work is going to end up being done in this map all regions call that I'm highlighting. The first thing that we have to do, we actually call the mapper to see what kind of task variant it wants to run. So make sure you pick a variant that's for the particular kind of processor, either CPU or GPU that we're currently about to map onto. And then once we've done that, there's some logging calls in here, some checks to make sure that we're not picking bad variants. We do a little bit of logging. And then what we're going to do is we're actually going to call this map all regions call. And this map all regions call is another one of the very important functions inside of Legion. It's what actually does the mapping onto physical instances for logical regions for all tasks. So I'll dig into that in just a minute. Map all regions call returns map success, whether or not we succeeded to map or not. If we did, or if we fail, if we succeeded to map, then we can no longer be stolen, so we can mark spawn task to false. We do a little bit of checking here to see whether or not we need to send information back to the origin, our origin processor where we actually started. So in the case where if we succeed to map and we actually have no virtual mappings, I'm going to skip what virtual mappings are today. In the case where we're remote, we actually want to send a message back to the task object on our owner node, the origin node where we originally existed, saying, hey, we actually finished mapping on a remote node, and here's the information about where we decided to map. And so that's what this send individual remote map call does. It ends up packaging up a bunch of information and asking one of those message managers to send back the information about where we mapped. Otherwise, if we failed to map, then we need to actually invalidate some of our state because we're actually, let's see, if we're not remote, I guess, this is issuing invalidations. I'm going to skip what that means today. We'll talk about that later. But if we did succeed to map, notice here's where we do our complete mapping call to mark that this operation has actually finished its mapping. So you'll remember that this is just a base call on the base operation class, which updates our state of our operation, saying that we finished the mapping stage of our pipeline. We've actually been able to map our task and actually have it run. And then we return whether or not our mapping succeeded or not. So just to show you a little bit of variation, there's also a perform mapping call for point tasks, which is the other kind of single task object. And you'll see that it's actually a little bit simpler than the individual task case. And the reason for that is that a lot of the logic that we saw in the individual task case is actually handled by the enclosing slice task object, which we'll look at probably next time. But you'll see that point task calls the same map all regions function to try and map all the different regions that our task is requested access on. And then we do similar things if our mapping succeeded and we have no virtual mappings, we tell our owner slice that we were able to complete mapping, and then we can actually complete our mapping stage of the pipeline as well. Let's actually look at this map all regions call real quick. You'll see that this map all regions call is a generic function. It's on a single task object. It's not specific to individual tasks or point tasks. It can be done for any single task object. And the idea here is actually very simple. The idea of this map all regions call is that we're going to try to map all the different region requirements that our task requested as part of its execution. There's a little bit of logging and checking up here at the beginning. We do some initialization before we do any mapper calls. The first and most important thing that we do is we haven't actually asked this mapper to map us before. If it tried to map and we failed or something, we're actually going to want to ask the mapper to map this task, which means the mapper is going to try to pick a ranking of memories of where to create the physical instances for each of our logical regions. So this is going to go ask the runtime to invoke the mapper, which will then go and call the processor managers that we talked about for the particular task that we're mapping onto, this current proc. That'll pick the right processor manager and then invoke the mapper for this task and call the map task mapper call, which will fill in all the fields on this object necessary for actually doing this mapping, picking a ranking of memories and so forth. At this point, what we do is we initialize a couple of different data structures that we're going to use for tracking, which regions have been locally mapped and virtually mapped and all sorts of special cases. But in the general case, we're just going to try to create physical instances for each of our different regions. So we have a big loop here over all of our different region requirements that I'm highlighting that shows we're going to loop over all of our region requirements and try and map each of them. We check to see if we've already mapped them in pre-mapping. We check to see if the mapper has asked for virtual mappings. If none of the special cases are true, what we do is we actually ask the region tree forest to actually try to perform a mapping based on the mapper's request. So we notice we're invoking runtime forest map physical region. It's going to actually try to map a physical instance of this logical region that we're requesting. And what we get back is a reference saying whether or not we succeeded to create a reference to a physical instance for actually doing the mapping. So were we able to actually create a physical instance for us to use? We check to see if we succeeded or not. If we succeeded, we're good. Otherwise, if we didn't, we set map success to false. We mark which region we failed to map, and then we can break out of the loop. Effectively, we only want to keep track of, we only want our tasks to be considered successful mappings if we mapped all of our regions. So once we fail any of them, then we know we're not going to try to map any of the rest of them. If we fail to map, one important detail is we actually clear out all of the mappings that we actually were tracking. This is important because we actually want to release the physical instances. We don't want to be holding on to resources if we didn't succeed to map. Otherwise, we can get into nasty cases with deadlock. And so we'll talk about that in some more detail later. If the mapper actually asks us to, we can tell them that we failed to map, notify them to tell them this task failed to map, in which case we've marked which region requirements have failed by setting this mapping failed flag to true. Otherwise, we succeed to map, and there's a whole bunch of operations that we do to actually go and actually finalize this mapping. The most important which of this is this register physical region call, which we do in the region tree forest. And effectively, this says we successfully mapped. So update all the physical instances with valid data, make sure they're all filled in and have good copies of the data for us to actually use when we run. And of course, if the mapper asked us to actually notify it, we can actually tell it about what the result of the mapping was. And at the end of this call, we return whether or not we succeeded to map or not. So we'll probably dig into this call in some more detail a little bit later about some of these special cases and so forth. But this map all regions call is where pretty much all of the mapping for every single task gets done, whether you're mapping locally, remotely, whether you're an individual task or a point task, it doesn't matter. We all go through this map all regions call, and this is where we're going to invoke the region tree and actually try to create physical instances for all of our different logical regions. So I'm sure we'll be back here at some point to actually dig into some of these calls in some more detail. Okay, the last thing I want to look at today before we wrap up is to actually look at one last call on lead that we were looking at earlier today. So if I jump back to single task trigger execution. Okay, recall that we have this launch task call, which is actually designed to launch a task onto a low-level processor after it's been mapped. You can see it gets invoked a couple different places inside of this trigger execution call that we were looking at earlier today. Let's actually look at what this launch task call actually does. Okay, this launch task call is another one of these very, very important functions inside of Legion, because every single application task that gets requested by an application will be launched using this launch task call. Again, it doesn't matter if you're remote or local, or whether you're running an individual task or a point task. It doesn't matter. We're going to, every single task that we're going to launch is going to go through this launch task call. So there's a bunch of different steps for actually launching these tasks onto low-level processors. And I've tried to annotate them as best I can. There's a lot of special cases and various things that we have to do here. And I'm not going to go into a whole lot of detail today, but I do want to walk through the steps just so you can see the high-level ideas of what's going on. So the first thing we're going to do is we're going to compute a set of low-level event preconditions for launching this task. So you see we're going to create this event, or this set of low-level events called wait-on events, which are all of the events that are low-level, or the task that we're about to launch needs to wait on before it can actually run. So what we're going to do is we're going to walk through a bunch of the different, we're actually check to see if, we're computing, what the set of the processor set that we're possibly going to run on, or, whether or not we're going to run on a particular processor. I'm going to skip over that for right now. But here we're going to have a loop over all of our regions. We're going to check to see if they weren't virtual mapped. If we actually have physical instances for each of these different regions, we're actually going to add their ready events. These are the events that mark when these physical instances have valid data for our particular task. Once they do, we're going to add, those events, those low events that we have, we're adding them onto our wait on events. We're also going to add wait on events for various kinds of locks and reservations and so forth that our application may have requested as synchronization primitives. These are pretty rare today, so really the main part is this adding these wait on events here. Let's see, there are special cases here for various kinds of physical instances. I'm actually going to skip some of them today. We also have cases where we need to add to wait on events for if we've requested futures as inputs to our task. We need to make sure that the futures have valid data. If we have reservation grants, if we have phase barriers, we all end up adding to this wait on events set of low-level events. Once we've done that, we can merge all these events together to get a start condition, which represents an event that's a precondition for our task to actually start running on the low-level runtime. There's a bunch of logging here to check for various things. We are doing some checking to see if we need to release any operations or release any reservations that we were taking. We then, step 2, I know this is a long function, so I'm going to try to fly through it here at the very end. I know we're almost out of time. We're going to set up the task context, which is setting up a bunch of data structures for tracking any sub operations that we're going to possibly launch once we start running. So I'm going to skip past a bunch of this. Step 3, we actually finally get to launch our task onto the low repository. So we do is we get a low-level runtime ID based on the chosen task variant that was chosen by the mapper. And then once we've done all that, what we can do is we can actually, let's see, let me actually find the launching call down here. There's a bunch of logging calls going on here to track a whole bunch of information about actually executing this task. But you see down here, eventually what ends up happening is we actually end up, that start condition that we created, we actually do a low-level runtime call to actually launch our task onto our target processor. So we spawn our low-level ID, we give ourselves a reference to this task, this single task that we're doing, which is what our Legion task wrappers expect. We pass in our start condition, which says, the set of all the low-level events that are preconditions for actually running this task. We give our priority based on what the mapper set it to. And once we've done that, we've actually launched our low-level, our application level task onto the low-level runtime. And then the low-level runtime is free to go about executing that task. So I know this is a big, complicated function. We'll probably definitely get into it in more detail at a later lecture. But at least you've seen that where this launch task call is, and you know that it exists, and that every single application task that gets launched in Legion ends up getting run or getting launched onto the low runtime via this launch task method. There's no other way that application tasks get launched onto the low level. Okay, so I'm over time. So for that, I'm going to wrap up today. Again, if you have any questions, send them out to the mailing list. And I think Sean will be back on Monday to actually do another low-level runtime session. All right, thanks again.